Hey. Good.
You have to download all of the data files?
No, you actually don't.
I have no disk space.
Don't do it.
I barely installed Conda and all.
Don't do it.
Okay. I'm gonna find a seat and hopefully you got enough volunteers.
We got none.
Alright, I will try my best. I'm just gonna
Okay.
get set up over there.
Okay. Thanks. Okay, welcome everyone. We're going to get started slowly while you're all settling in. So this is the TensorFlow workshop, and I am Amy, and this is Eli, and our colleague Julia was not able to make it at the last minute. So we will be your guides for this, and we're sort of going to swap off on being TAs. So while one of us is speaking, the other will be wandering around. So there's some. This is meant to be an interactive workshop. So I'm glad to see that pretty much everyone has laptops. But I also sort of wanted to emphasize that if something's not working for you, or you just don't have everything installed or whatever, don't stress about it. So we specifically designed this workshop so that everything that you need is in the GitHub repo, and you can go find it in the slides, and you can go find it and just poke around at your leisure. So I know it's going to kind of seem like perhaps a fire hose of information, but everything's structured so that you can go back to it, and there's like resource links for everything. So don't fret if it kind of seems like too much of a fire hose. So let me first get a sense of who has done the installation already. Oh, wow. Amazing. Okay, that's fantastic. In fact, I couldn't really tell who didn't raise their hand. Who needs a little time to do the installation? A few people. Okay, yeah, we planned just a few minutes in the beginning for that. Okay, great. So here are on this slide, here are the two links that you sort of need to get started. One is to the GitHub repo that we're going to use, and the other is to the slides. So if you have these, you should be good. All right, and we'll come back to these links. As you might be able to tell, they're also on the footer of each slide, in case you forget them. So before I get started proper, there's too many of you to go around the room, but let me kind of take a poll. How many of you do a little bit of work with machine learning or data science? Oh, great. Okay. How many of you are familiar with Docker and have played around with Docker a little? Great. How many? Okay, here's where we get into unknown territory. How many of you are familiar with Kubernetes or have played around with it a little bit, or even know what Kubernetes is? Okay, good. We have a section at the end where we're sort of just going to give a Kubernetes demo. You can play along if you're comfortable and familiar with it, and you'll get a lot out of it just by watching if you're not. Okay, great. So let's plunge in, and we'll those of you who still need some setup time, we'll give you a little bit of time in just a few moments. So here are some of the things that you'll learn in this workshop about TensorFlow. You'll learn what TensorFlow graphs are and how to build them, and learn the data structures and concepts that are related to building and running these graphs. You'll learn how to save and checkpoint models, TensorFlow models that you're training, and how to reload them later. We'll show you something called TensorBoard, which is a really nice dashboard for doing debugging and exploration of your the variables of your graph while you're training it. And we'll also give a little bit of an intro to the TensorFlow distributed runtime. And I realized I forgot to, when I was sort of polling you earlier, I forgot to ask a very important question. Who is familiar with TensorFlow to some extent already? Just a few of you. Okay, good. Because this is probably going to be a pretty basic workshop with respect to that. So I'm glad that there aren't a whole slew of you who are already familiar. So from a machine learning perspective, so this is actually not really a machine learning workshop per se. It's sort of more a TensorFlow workshop. So we don't have time to get too deeply into machine learning concepts. But that said, we'll do some fun things anyway. So we'll start by looking at how you would build the sort of the hello world of neural nets, an MNIST example in TensorFlow. And then we'll also look at building a word-to-vec model. So this is building a neural net to learn vector representations, word embeddings for words. And we'll talk about what that means and what it's doing. And then if we have time, which I kind of suspect we may not, we'll look at building a convolutional neural net for text classification and using the learned word embeddings that we learned from the word-to-vec part of the workshop. So I kind of think we won't have time for this, and we will probably have to just point you to the GitHub repo and where there's a lot of instructions. And then finally, we'll demo TensorFlow's distributed runtime running on Kubernetes. Okay. And I've essentially just covered all that. So we have a break that's fairly mandatory at 3. Mandatory meaning that's when the food comes out. So I almost set an alarm on my phone, but everyone, please just give me a heads up when it gets to be 3. Just wave and tell me it's 3, and we'll stop, so you don't miss the food part. Okay, so let's take just a few minutes, like 5 minutes or so, to see how people go with this setup. And those who are already set up can maybe poke around a little in the repo if you want. And Eli's in the back of the room, ready to answer any setup questions that anyone has. We can also help you set up during the break, too. Yeah. Probably the easiest thing to do would be to run one of the little starter scripts that we'll look at in a minute. So if you go into the, if you've cloned the repo and you go into the, under the workshop sections, the starter tfgrep subdirectory, and try to run one of those little scripts. And if it runs successfully, you're probably in pretty good shape. All right. And I believe some feedback we've gotten from people when we've done this before, I believe that if you're on a Windows machine, you'll probably have better luck with the Docker file. In fact, that's what sort of prompted us to build the Docker file. So that is probably the route you should take if you're running Windows. Actually, no, it doesn't. It'll do that for you when you start it up. You'll want to clone it for some of the Python scripts that we're going to run. So, yeah. In fact, the data is not included in the repo. Eli? There's a question.
Would you recommend using, would it be possible to use TensorFlow from within a Jupyter notebook? Is that
Yeah. Yes, and in fact, we have an example of that.
Okay.
Yeah. You just need to just start up Jupyter like within your environment if you, yeah. The question was, can you run this stuff in a Jupyter notebook? Yeah, and we have an example of doing that. Okay, I'm trying to guess from everyone's expression if you're all set up or not. Turns out that's sort of hard to do. Who feels like they need another minute or two? Is everyone? Okay. Let's give it just a couple more minutes and we'll get started. And again, there'll be time during the break if something's just not installing right. Oh, but by the way, the guy in the blue T-shirt taking a photo of the screen, he's like a ringer TA. He can help with, this is Wes, he can help with Python-related questions, although not necessarily TensorFlow-related questions. So if anyone has a Python or installation-related question, give him a wave. Okay. So again, there'll be more time during the break if anyone's a little bit wedged on getting stuff installed. So we'll do just kind of a very brief intro to some machine learning and neural net concepts for those of you who aren't familiar, and this will be too basic for those of you who are. so first, what is machine learning? I'm actually not even going to attempt to answer that question. I think you could probably ask 10 people and get 10 different answers. But one good sort of canonical answer, perhaps, is that it's a field of study that gives computers the ability to learn without being explicitly programmed. And of course, if you sort of delve into that, you're thinking, well, what's explicitly programmed mean? And there are kind of levels as you go down. But I think I won't delve into it too deeply, and just comment that machine learning is sort of experiencing, I think, a resurgence of popularity, and so there's a caution that comes with it. You know, it's not a panacea for everything. And this is quite an interesting paper if you haven't run across it. Not to knock machine learning, but. All right. So let's talk just a little bit about neural nets. So this is kind of like a canonical, very simple feed-forward neural net structure where you have inputs and you have outputs. You have some number of hidden layers. The nodes of the net contain activation functions, and the connections between the nodes have weights. And so typically you're learning those weights, and you can learn categories. You can do linear regression and learn essentially continuous values, like what's shown here, and your inputs might be, for example, text, might be images, might be anything. So as anyone who does machine learning knows, figuring out your input features and cleaning them up is kind of a huge thing that we're not even going to get into during this workshop. And so typically, many neural nets learn using something called backpropagation. So the idea is that you take your input, in this case a cat picture, you run it through your network, and you compare the answer you get with what the correct answer should be, and using information about the difference, you adjust the weights of your connectors in a direction towards addressing that difference, essentially. And you do this working backwards from your outputs to your inputs. So that's where the name backpropagation comes from. And we'll show in a little bit, like how do you do this in TensorFlow. Okay, so most neural nets don't just look like this. And in fact, this schematic here is kind of like an abstracted view of the Inception 3 image classification graph that came out of this is Google's effort in one of the ImageNet contests. So this is, I believe, about 40 layers, 40-some layers big, if I remember correctly. So when people talk about deep learning, they're typically referring to networks which have many hidden layers and look a lot more like this than that cat-pictured neural net that I showed earlier. Okay. And that's actually all I'm going to say about that, and there's links to a lot more resources if you want to sort of delve into that a bit more. All right. And feel free to interrupt me with questions if you have any, and prompt me to repeat the question if I don't remember to do that. Okay, so what's TensorFlow? Well, at a high level, tensors are n-dimensional matrices. And so TensorFlow lets you build flow graphs, where the nodes in the graphs are typically operations, although they can also be things like inputs and outputs and variables. And the edges, so this is a directed graph, and the edges of the graph support, the edges of the graph connect input and output of the nodes, and tensors, these n-dimensional matrices, essentially are the content carried on these edges. They effectively flow along the edges, which is where the name of TensorFlow comes from. And so it's an open source project which was open sourced late last year. And it has a lot of nice features. It is, we believe, intuitive, flexible, easy to use. You can define your own high-level operators. You can define your own custom operators. It supports automatic differentiation in the sense that you can build a graph that describes your predictive model, and you can add to that graph information about what your objective function is, and then just tell TensorFlow, well, optimize with this. And so you'll see some examples of that. It supports, has a lot of support for doing asynchronous processing, and you can train it on CPUs, GPUs, and of course, now we are excited to say, coming soon, TPUs. I don't know if anyone caught this announcement. I think it was last week. That Google has been working on something called tensor processing units, and these are not available yet. Those are chips optimized for tensor processing that are faster than GPUs for that purpose. So these are not available yet for everyone to use, but soon, with air quotes, soon they will be. So we're very excited about that. Okay, and this is just an attempt to emphasize in two-dimensional space what an n-dimensional tensor looks like, which is hard to do. Okay, so some of the core concepts in TensorFlow, and this is by no means an exhaustive list, but you'll see all this when we start to get into the exercises. So there's the graph, a TensorFlow computation. So you can think of it as a collection of ops that may be executed together as a group. There's an operation, so that's a graph node that performs some computation on a tensor, these dynamically sizable n-dimensional matrices. And then there's tensor. So in the sense of a TensorFlow data structure, a tensor is a handle to one of the outputs of an operation. And so you'll see what I mean by this when we start to build actual graphs. So it provides the means of computing the value of a tensor in the context of a TensorFlow session. So again, that'll become concrete very soon, and you'll see what I mean. But there's deferred execution going on. So you define your graph, and it kind of looks like as you put your graph together, it'll kind of look, in the sense of, Python statements, that you're actually doing the computation, but you're not. And so if you try to access a tensor at that point, it won't have a value in the sense that you're looking for. So you need to evaluate or run your graph in the context of a TensorFlow session to get tensor values. And again, we'll see that. Okay, so some more core concepts. Constants, placeholders for input. We'll see what I mean by this. Variables, modifiable tensors, and then session. So this encapsulates the environment in which you're running these operations and in which your tensors are evaluated. And just to kind of give a sense of the range of operations that are available. There are a whole bunch of different categories with, make sure I don't blind anyone as I fire up my laser here. We'll look at a lot of the neural net building blocks when we go through the exercises in this workshop. And just to remind myself to mention this, when you look at the TensorFlow documentation, things are structured according to kind of a subcategory of what they do. And so I find it to be kind of a nice way to explore. So I have these queued up. This is from the TensorFlow documentation at tensorflow.org. And I don't know how well you can see this, but this is the neural net page, nn.html. So first in the list is all of the activation functions that are supported, for example. So again, these are subcategories of operators. And I think when you're just exploring TensorFlow, it's kind of useful just to go to this page and just search for things that you're interested in and see what comes up. Kind of similarly for the training, this is another subcategory of operators. Like for example, the optimizers. Here are some of the optimizers that TensorFlow supports. So just poke around. Look for things that you're expecting to see just by searching on these pages. It's a good way to explore. Okay. All right. Time for some hands-on stuff. So this is just to get our feet wet and play around just a little. Go to the subdirectory in the GitHub repo that's called, under workshop sections, it's called starter TF graph. And I will take this opportunity to make sure that everyone can see my font size here. How does this look to people? Okay-ish. Okay. All right, so this is just kind of a very basic sort of playing around first TensorFlow graph. So here's what's going on. First of all, we're defining a constant here, m1. And maybe I should just make sure that everyone's oriented. So that this is in the GitHub repo that we had you clone under workshop sections, and then a subdirectory called starter TF graph. So if anyone got lost there, wave your hand and Eli will come and assist you. Okay. So here we're first defining a matrix that's a constant, and then we're doing some things in the context of this default graph. So we're creating the graph by these statements inside this context here. So we're not running anything yet. We're defining the graph. Okay. And this I believe actually is unnecessary now. This subcontext. I don't believe that these statements actually need to be pinned to use a CPU, although probably that's what all of you have anyway, so no harm done. Does anyone have things set up to run with GPUs? Yeah, me neither. All right. So here we're defining a variable called m2.
Are you saying that isn't actually anything? I mean, it is
Yeah, it's not necessary, is what I was saying. The question was this necessary? This I believe is actually a cut and paste error from an operation, particularly or specifically an embedding lookup operation that need to be pinned to use CPUs, and so that. I believe this is actually a cut and paste error that should be removed. In other words, if we had GPUs, this would run fine on GPUs. But we don't have GPUs. It'll always work on a CPU. So this is sort of an unnecessary pinning is what's going on here. It was not necessary to restrict this code to run only on CPUs. Yeah, but that's how you would do it. Yeah, and there are some things you do need to restrict. Yeah. Okay. So we're defining a variable, M2, a matrix. We're giving it a shape and initializing it with random uniform values. Then we're doing a matrix multiplication here. And again, this is just our graph. We haven't run the graph yet. And then we're further building the graph by adding this print operation. And just put that in there because it's a nice, useful debugging operation to know about. So you'll see when you run this how it looks. So if you're trying to figure out, oftentimes you're doing a series of operations and you're just trying to figure out like sort of what shape do you have of things at some particular point. It can be useful to do that.
Played with NumPy so they know what this shape thing is? Great. Okay, I just
good.
wanted to make sure we weren't leaving people in the dust.
Yeah, sorry about that. Great. Yeah, this is designed to, as you can tell, to look kind of NumPy-like. And in fact, you can very often just pass in NumPy variables, as we'll see here, without doing anything particular to them. Okay. Then still in the graph context, we're going to initialize all the variables, which is necessary before we start running the graph inside our session. Okay, so now in the session context, and you notice we're passing the graph into this session context. First, we're running the variable initialization here. And then we're first doing some printing of things, so we'll come back to that when I run this from the command line. And then here's something that's useful and important to pay attention to. This line is constructing a dictionary of input values that we're going to map to the placeholders that we defined. So we, up here, we define this input placeholder. And so here, we're creating a dictionary where we map that input placeholder to this M1 constant that we defined earlier. Okay, and it doesn't have to be called feeddict, but it almost always is when you look at examples, just because that's kind of a convenient convention. So when you're looking through a lot of the examples on the TensorFlow site, you'll see this. And then here's where sort of the crux of it here. Now we're actually going to run our graph. And so we're passing it this feeddict dictionary to the feeddict arg right here. Okay, so that's mapping our inputs to the placeholders we defined. And then we're specifying in this list here what we want to evaluate. So you'll see this over and over again in TensorFlow code. You know, we've defined this graph, and we want to evaluate different parts of it, you know, at different times for different purposes. And so what we're doing here is we're saying evaluate M3. That's part of our graph. And we get the result, and we print it. Okay, so let's see how this looks when we run it. And this is also, if you haven't already, this will be a good sanity check to see if your environment is set up okay. So if you set up a virtual environment and you're starting a new shell window, remember to activate it in that shell, of course, first. Okay. Is that big enough for everyone? A little bigger? Okay. So here's what we're getting as output. So notice these two lines, M2, and then eval M2. So we'll go back and look at the code in just a second and see what's going on with that. And now this is our print debugging statement happening here. So it's letting us get some information about M3, and then here we're printing the result, which again is M3. Sorry?
Can you go back, scroll back to the command line?
Yeah, okay, yeah, sorry. Yeah.
You're missing the top row on the projector.
Right. Okay, yeah, I'll try to remember that. Give me a yell if I don't remember that. Okay. Okay, so there's something kind of interesting happening with the M2 print statements. So let's go back to the code and look at what was going on with that. So here we're just printing, the first print statement, we're just printing M2. And this is not gonna get us the values of M2. So you remember I was talking about that deferred execution, right? That's just printing M2 as a variable, but it's not giving us the contents of M2. So to get that, we can eval it in the context of this session. So in the context of the session, we can eval it. Or we can, similarly, we could call session run on it. So if you, typically you'll see session run used when you're doing an evaluation where you want to pass in inputs, right? Because this allows you to pass in the mapping of your input placeholders. But sometimes it's sufficient just to call eval within the context of the session. And remember, we pass the graph into the session. So it kind of you'll see both when we look at the code. It kind of depends on what you're doing and what information you want to get. Okay. So now let's have you guys do a little bit of editing of that and see if you can add a little bit of stuff. So try without looking at the answer. Try doing something like adding M3 to itself. Store the result in something like M4, and then on that session run call, passing in a list of both M3 and N4 to be evaluated. I'll just give you a little bit to play around with that, or do something similar. Just play with editing that code a little bit, and then we'll look at how you can do that in just a second. Just add will do. Yeah. Add will work. Yeah.
What does the mat mean instead of mul? Because I see there's also just a mul for multiply under operations.
I'm actually not sure of the answer to that. We'll have to look at the docs. Yeah. I think it's broader. Yeah. Yeah.
Operations, there are some operations that are gonna like mean different things if you're doing them to two. So like if you can imagine like inferring that a scalar is a tensor and then doing a mat multiplication with like a scalar and a tensor, you're gonna get a shape error, right? If it's like a single thing. So you want that to be unambiguous, is like you're multiplying a scalar by a tensor. That means you want to do element-wise multiplication rather than getting a shape error if you were doing matmul, which is why there are two different functions.
Okay, let's take a look at the results, and you can mess with this further later if you weren't quite done. So this is just one way you could do this. It was a pretty open-ended exercise, and this is looking in the same directory at matrix mul add.py. All right. So here we are defining M4. So this is creating another node in our graph. So M4 is adding M3 to itself. So we just added another node to our graph. And so when we go to run the graph in the context of the session, we can do something like this instead of what we did before. Before we passed just one element in the list, M3, and said evaluate this. So now we're saying evaluate these two items, M4 and M3, and give us the results. And these results are in the order of the arguments passed here. So, and then we're just printing the results. And so I think this is kind of useful in showing that there's sort of, when you're thinking about running these graphs, you can evaluate any part of the graph, in the context that you want to do that. There's no sort of like one entry point or end point to these graphs.
Out of curiosity, is there any advantage to doing everything in a single session versus just doing multiple sessions and generating the results? Like if we, instead of putting in a list of M4 and M3, we just put like, we run one session of M3 and one session of M4.
In this case, no, but if you're doing training and you're updating your variables, then yeah, it would matter then. Yeah. The question was about using multiple sessions versus just one session, and so in this simple case, it doesn't really matter.
If you're evaluating M4, so you define the graph at the top. And so M4, is that essentially saying you have to evaluate M3 to define M4, so then you evaluate M3?
Yes.
And then so it'll go back up the chain until anything that's used to define M3, then it'll go backwards through.
Yeah. So it propagates through the graph and essentially processes what it needs to answer your question.
Lazy evaluation.
Yeah.
If the evaluation could have been once, does it store states evaluated?
That's a good question. Does it cache the results of the evaluation? And we were asked this before, and we even had a TensorFlow expert in the room with us, and he did not know the answer to that question. So it seems like you might expect that to happen, and I'm afraid, unless you know, Eli.
Was this the caching question?
Yeah.
Yeah, I went and tested this
Oh, okay,
the other
good.
day, and
Good.
it does not cache. So if you evaluate something, it's going to run everything upstream. And I suspect the reason for that is because you want to be able to evaluate things multiple times. So like the training ops, you want to be able to evaluate multiple times and have them like different things happen.
Mm-hmm.
Like if it cached them, then you wouldn't be able to like do the iterative training process with just evals. And I think session is just supposed to be a wrapper around evals.
Makes sense. And another thing, just to kind of hammer home about this example, is that it shows that here we're doing all of this definition here in the context of this default graph, and so even though we're not mentioning the graph as we add this line, this is adding a node to this default graph.
If I wanted to save computation, could I evaluate through M3 to capture the result and then feed it back in M4? Feed the result and then back into M3 to capture M4. See that evaluation step.
Well, to answer your question a little more broadly, it is possible to checkpoint and save all of the variables of a graph, and we'll see that a little bit later. So that's a common thing to do during like a long training session, is periodically checkpoint, and then you can load those later, which essentially gives you what you want.
On M3, does that node have two operations?
I'm sorry, does the node...
So M3 equals TF dot map matrix multiply, and M3 equals TF dot print. Why are there two things?
Oh, well, in this case, it's kind of a weird identity op. Yeah, so that perhaps the not very helpful answer is that's how print works. Yeah.
In the actual execution graph, it'll be like a node and then an edge, and the outputs of the print node will be the same as the inputs. So that's what Amy means by identity op, is that it just doesn't manipulate the input at all. But there will actually be a node in the graph there.
Mm-hmm.
And so M3
Yeah.
in this sense is like overloaded. It's like a pointer we overwrote. So
Yeah.
it's like
Yeah.
a pointer to the mat mul op, but then we just made it the pointer to the print op because those things are equivalent.
Can you just run the print off without assigning it to
You just
Y-
run
you-
the...
yeah, or assign it to a differently named variable, for example. Yeah.
Yeah.
So M3 has essentially two operations, or is that you combine it one time and then if you want to print it, that's
So you're in a context here, right? So all of the graph is keeping track of all the operations. The outputs of the operations are those handles that Amy was talking about. So I think it maybe makes more sense to think of M3 as a pointer to an operation.
Mm-hmm.
And so we're overwriting it here.
Yeah, we're reassigning it. So it probably would be more clear of an example if we didn't do that and we named the print assignment some other variable name. Yeah. Okay. So, moving on to building neural nets in TensorFlow. And we're actually not going, I'm just going to walk through some stuff on the slides for this section. But if you want to go play with it yourself, go to tensorflow.org and look for the MNIST tutorials they have there. And you can do a little bit more hands-on with this. We'll get more hands-on when we go to the next section, which is Word2Vec. But here we're just sort of going to look at like what's the structure of a simple kind of hello world like neural net. So the MNIST task for those who aren't familiar is number recognition. So you have a bunch of images that kind of look like this that humans are pretty good at identifying, especially if you know that these are supposed to be numbers and not letters. We're pretty good at telling what numbers those should be. For computers, it can be a little harder. So this is kind of a canonical neural net problem that a lot of people try to solve in different frameworks. So what you have is a bunch of these images with information about the so they're black and white images. So information about what pixels essentially are on and how dark that pixel is at that point. So what we want to do is we want to build a little neural net that we can train to recognize these images. So we have a data set that has a bunch of labeled examples. So we have a bunch of images, and we know what they're supposed to be. So we'll be able to use that for our training. Okay. So if I go through this kind of too quickly, because this part is not hands-on, so if it seems like a bit too much of a fire hose of information at this point, just remember there's a really detailed tutorial on the tensorflow.org site that goes into this too. Okay, so the first thing that we're going to do is create a placeholder, or yes, oops. I can't click on my slides, can I, without advancing them. Create a placeholder for the input that we're going to give it. Okay, and we're defining some variables, weight and bias. And I'm going to sort of skip over the matrix size calculations that we're doing here. We're going to essentially flatten the image in this case when we do the input. So we define our input placeholder. We initialize the variables. Okay. Here's the model. Placeholder for the correct answers. So here's our labeled results, and here is the model itself. So softmax, without going into the details, this is essentially going to let us get a probability distribution for the results. So we want to answer, is this a number from 0 to 9, essentially? Is this a digit from 0 to 9? And softmax is going to let us generate a vector that has the probabilities of the thing we saw is, X% a 0, X% a 1, etc. So this is our model right here. And I'm sorry, my laser pointer doesn't reach all the way over there. But we're doing a softmax operation on our input images. We're flattening the input images multiplying that times the weight matrix and adding the bias. Okay, and then in this case, we're going to define our loss function like this. Okay, and so this is maybe kind of an interesting aspect of what we're doing. This is just another node in our graph, right? Defining the loss function in terms of our model. And then here we're defining how do we tell if what we came up with is correct. And we're using something kind of a nice handy operation called argmax, which will give you the indice that has the highest value along the dimension that you specify. So that's basically a way of, we've got softmax generating this vector of probabilities. We're going to pull out the highest probability, and we're going to compare that to our label information, which is also a vector and says, which, with the index of the thing that it actually is set to 1 and everything else set to 0, the so-called one-hot encoded labels. Okay, so we're building something essentially that looks like this. The top figure is the sort of the neural net-like version of it, and the bottom figure is the mapping it to the matrix operations that we're doing. Okay, so here's the slide where the power of TensorFlow kind of comes into play. So we defined our loss function here. It's that cross entropy variable. And now we're just going to say, let's use a gradient descent optimizer. And we're just adding another node to the graph when we specify that. And we're going to tell that optimizer to minimize that loss function that we defined, the cross entropy variable. So it maybe is a little hard to tell as I step through these slides, but this is all in the context of defining the graph. Okay, so what's kind of going on behind the scenes here is TensorFlow knows what this graph is. So basically, it's automatically using backprop to determine how your variables affect the cost that you've asked it to minimize. And so then it can apply the optimization algorithm that you've specified to reduce that cost. Okay, so all of that was just defining the graph. So now we're going to run the graph. And do some training. So the sort of the crux of the training is just this line right here, session.run. So we're passing it in the map that maps to our input placeholders, and we're saying run this training step, which, if you remember, was just this graph node here. The train step is running the optimizer minimize op. So by telling TensorFlow do session run on on that train step, it's doing an iteration of training with the little batch of data that you've passed it. And then the stuff below is just saying, like, well, how did we do? Okay, and so this is actually kind of a common pattern, incidentally, that you can look for when you're looking at TensorFlow code. You'll see people they'll build the prediction or inference part of the graph. Then they'll add nodes to it that essentially define the loss or the cost function that you want to use. and then they'll define the optimizer and how it relates to, do you want to minimize the loss, for example? And again, those are just building up nodes in the graph. You'll often see people sort of pull those apart into separate sub-methods just to kind of keep their code tidy. But you'll see this pattern. Okay, and then for context, then here's the whole process. And I'm not sure how well you guys can read this. It's kind of small, but you can look at it in the slides later. So we're defining the input placeholders, and we're defining the model. Y is the model node, essentially. Defining the loss function that we want to use, the optimizer that we want to use, and then the training step is to ask the optimizer to minimize that loss function. And then, again, that's all the graph setup. And then we're running iterations of training. So does that kind of make sense to everyone? And it should make sense to you without knowing like exactly what softmax is, for example. You don't need to know that to sort of get the gist of what's happening here. Okay, great. And again, there's a whole tutorial on this if you want to go and kind of look at the gory details of all of that. All right. Let's see. How are we doing on time? Okay, great. So are there any questions so far? Okay. So let's look at something kind of fun called word dev. So this is kind of a neat idea. So if people are trying to do natural language processing, it doesn't work very well because the semantics are very poor if you just take sort of the naive approach and just assign, say an integer to each word that you want to have as part of your corpus or whatever. So, cat is 1, dog is 2, whatever, tree is 3. Doing that, assigning those discrete values to your words is very information poor. It doesn't tell you that dog and cat are both mammals, both pets, and they're kind of semantically closer to each other than, say, cat and computer, or something that is not very semantically related to a cat. So people typically try to address this in with 2 different categories of approaches. And so one, and let me take a step back here. If this is just all kind of meant to be kind of interesting background, if this is like too much of a fire hose of information, do not worry. It won't impact your ability to play around with this exercise or do the rest of the workshop. Okay. So there's sort of 2 categories of approaches that people tend to take, and one is off to generate vectors for words so that similar words are nearby each other in the vector space. And so one approach to this is a so-called count-based approach, like latent semantic analysis, for example. And the one that we're going to talk about here is using learned embeddings. For example, using a neural net to learn the vector representations of the word, often called the embeddings. So basically what we're going to do is we're going to take just a big corpus, I believe it comes from Wikipedia, of just a bunch of sentences, and we're going to learn just from processing that data word embeddings that give us the neat result that words that are semantically close to each other, they're going to have these vectors. Their learned vector embeddings are going to be closer to each other than words that are not so related. Okay. So if you look at the literature, there are kind of two ways that people approach this. One is often called continuous bag of words, and that's people learn these embeddings by predicting target words from source context words. And the thing that we're going to look at in our exercise does the reverse of that. It's called skipgram, and it predicts source context words from target words. And that's, again, that's not super important to keep track of. So the technique that we're going to be leveraging for this is something that a relatively recent research development. People have figured out, well, we can get we don't actually have to generate a full probabilistic model as we try to do this. That is pretty expensive. So instead, we're going to do something. We're essentially going to use logistic regression to, this is a neat little trick, to discriminate target words from basically randomly selected noise words, and that's going to be a lot cheaper, and that actually gives us pretty good results. So this, again, this is sort of a research path. There are papers that you can read to find out more about this. So this is a nice little trick that will let us learn these embeddings relatively cheaply. And the technique is often called noise contrastive estimation loss. And TensorFlow happens to have an operation for that we are going to use. So the graph that we build is actually going to be pretty simple. Okay, so that's just all background. And so what we're going to be doing is we're going to be taking the so-called skipgram approach, where we take this big corpus and we kind of have a sliding window along it of context target pairs. And so we're going to take a window size of 1 in both directions and predict the context words from the target word. And I always get this reversed, so I have to crib from my slides here. So, for example, if you have a sentence, the quick brown fox jumped over the lazy dog, then the context, in this case, we're just using a window size of 1, and typically you would use a larger window, which would, of course, make your training more expensive. But here we're just using 1 in both directions. So, for example, for quick, that's our target. Our context is the and brown. So you can see that indicated here. And then for brown, our context is quick and fox. Again, I apologize, my pointer doesn't really reach all the way over there. Oh, it kind of does. All right. Okay, so that gives us our input-output for training, right? For our target words, for example, quick, our context words are the and brown, etc. All right. And so before I show you what the code looks like for this, here's what we're going to end up with. And at least if you run it long enough, we may not be able to run it long enough to see extra excellent results. But here's the kind of thing you can end up with. You can learn. So again, we're learning these word embeddings so that similar words are nearby each other in the vector space of words. And so that lets us do things like find analogies or find words that are similar to a given word. So for example, we can answer questions like, if say we have if we have king and queen, and then we give you the word man, how would you sort of fill in the blank there? and you can guess it would be woman, for example. Same with verb tense. Same with answering questions about given a country. Like say, if you give China and Beijing as a pair, and then you say Japan, can you infer that the answer should be Tokyo? So it's really cool to see this run, and it's not very expensive, which is the neat thing. You'll be able to see it as you do this exercise. Okay, and here are some actual results that I generated, just for a little bit of reality check. So the first column there is asking what's nearby to cat. What vectors of other words are near to the cat vector, and I got this set of results. In case anyone is wondering what Avner is, it turns out to be the name of a guy who did some body modification to look like a cat. So it's very appropriate that he's in that list. And then the second one is running the analogy. If I give you cat and kitten, then I give you dog, what's the analogy? Pup, and it got puppy. So again, very fun stuff. All right. So, and you can do it without taking too much time, amazingly enough. So let's go to the GitHub repo and now look into the intro word to vec section. Okay, and let's start the training jobs running, and then we'll take a look at the code, because it does take a little bit of time to train. And there are two ways that you can do this, depending on your preference. You can either just run a script from the command line, or you can start up a Jupyter notebook. And so I think when I run it, I think I'll run from the command line just because I think it'll work better in this context. But to show you how to start up a Jupyter notebook first, you can just say, so change to the intro word to vec directory. You can just say Jupyter notebook, and it'll pick up what's in the current directory. It'll start a little server. Okay, so here's the point. If you're running in a Docker container and you're using Docker machine, you might have to do a little bit of sleuthing to find your IP instead of localhost. Who is doing that? A few people are. Okay, good. So what you'll need to do is go outside Docker on the command line and do docker-machine IP. And let me just type that in so you can see. So just, again, outside the container, if you do Docker machine IP, it should give you an IP that you should hit instead of localhost to see your Jupyter notebook. And you want to be on port 8888. And just give a yell to Eli if you're having trouble with that. So people who are working in a virtual environment, it should just like pop right up for you on localhost. Okay. So this is just a list of the current directory. Let me make that a little bigger here. And click on this notebook here. Okay, and if you're not familiar with IPython, you basically can just step through the cells in this notebook, either one by one, or you can run them all at once. And this is what the icon looks like to run that cell and then select the next one. And if you're doing that, just make sure that before you click from cell to cell, that the current cell has finished running.
And I believe there's a typo in the notebook, so you will need to add the import URL retrieve from URL lib import URL retrieve, not URL lib2.
Oh, sorry. I tested this too.
No worries.
Yeah.
Is TextDate.zip one of the libraries, one of the data sets that you gave us to download?
No, the question was, should you already have TextDate.zip downloaded? No. It's sort of, it wasn't clear whether we could sort of just bundle it, whether we had the rights to bundle it, so we just left it for you to download. But it's only 30 meg, so it shouldn't be too bad. Although if you all hit it at once, it might cause a bit of a lag on the Wi-Fi, but it shouldn't be too bad.
Okay, just like a bunch of things that you said, like your right?
Yeah, yeah. This doesn't actually require any of those yet. Yeah. So
On the URL retrieve?
sorry, what was the typo, Eli?
URL retrieve from URL lib import URL retrieve.
Okay. All right, and I am going to, actually, before I do that, let me just scroll down. So what the contents of this notebook are basically doing the graph setup and then and defining some methods to do the pre-processing of the input data, and then the actual training step, which is going to take by far the longest, looks like this. Look for the begin training comment here. So this is the thing that's going to take a while. So once you get down to that cell and start it up, we'll let it run and look at the code. Okay, and I'm going to do the same in the shell and just start this running as a command script instead. Okay, and you can do that by running the word2vec basic summaries.py file. And this file, so if you look at TensorFlow.org, there is a word2vec tutorial, and this is a modified version of the script from that tutorial. What we've done is we've added something called summaries, and I will show you what those are good for shortly. But other than that, it's essentially the same code that comes from the TensorFlow.org tutorial on this. Okay, so I'm going to start this running. Okay, and you'll see this in the IPython notebook as well as it runs. You'll see that it picks, so it does its initial data processing, and it picks a random set of words to track the nearest words to as it does its training iterations. So when it starts out, you'll see these this nearest to list. This is going to be completely random looking initially, because what it's doing is, as we'll see when we look at the code, is it's doing a random initialization of these embedding vectors, and now it's learning to make them better and better. And as everyone hits the download link to this this data file at once, you might be just a bit slow to start up. So I'll give you all a minute to do that, and then start your own training iterations running, and then we'll take a look at what the code is doing. Okay, actually, let me just jump to looking at the code. And hopefully everyone will eventually get that file downloaded. I killed my Jupyter server, so it's complaining. Okay, so what's going on behind the scenes here? And it's kind of a testament to the power of TensorFlow that it's actually not all that complicated. So first we're defining, and you can look at this in the code as well. It's the same thing. So here we're defining a set of placeholders for. So we did this data pre-processing. So we did all of the the parsing, the context target pairs, like we talked about, with this moving window. So we've done all that. We've generated our data, our labeled data, and so we're building placeholders for those. And then valid data set is that's short for validation. little confusing nomenclature there. So that's just that set of things that we're printing each iteration as we train to see what the nearby words are. So we pick a set of words and we stick to it. Okay. And here again, we're pinning to the CPU. This is actually required here because I believe it's the embedding lookup op that doesn't work with GPUs. So it's saying do this part of the graph with using CPUs. So we're defining an embedding variable, and then embedding lookup is kind of a neat op that's saying basically just take the train input slices. So we've got this big embedding matrix for all of the words in our corpus. I believe it may cap at some large number, but basically all the words that we're training over, we're building a big embedding and learning a big embedding matrix for those. And so embedding lookup says, given the train inputs in this current batch, what's our embeddings for those? Then we're defining the weights and biases that we're going to use for this NCE loss function that I mentioned previously. Okay. And you can see that that we're just initializing the weights to truncated normal and the biases to 0. Okay. Now here's the part where we're defining the loss based on this NCE loss operation that I was talking about, and you can go look it up and read in more detail the details of how it works. But we're passing it the weights and biases that we defined, the embed as the input, so that the embed was the lookup in the big embedding matrix of our current batch, our train inputs. Okay, so we're passing all that to this NCE loss operator. Then we're saying use gradient descent as our optimizer and minimize this loss. And that is all that we need to do to define this graph, to train this network, because the NCE loss operator is doing a lot of powerful stuff under the hood. Okay, and then our training iteration just looks like this. So, something I didn't really talk about too much was part of the pre-processing involved a bunch of generation of mini batches. So we're essentially just kind of iterating through all these generated mini batches. And for each one, we're initializing this feed dict for it that says, here's our mini batch inputs. And then we're just doing session.run and saying evaluate the optimizer and the loss nodes in this graph. And so if we look back at what those were again, it's the evaluation of the optimizer, of course, that is going to be doing the actual training for us. And the loss is the evaluation of the loss. We're actually going to use that to print some updates as we iterate through our training steps. So it's important to evaluate the optimizer. So that does the training step on the mini batch. But we don't really care. We're throwing away the result of that because we're just triggering the training step. We don't need to see the result of that. We are interested in the loss because that is what we're printing here with the average loss. We're actually not printing the loss and nearby information at every single training step, which would be expensive. Okay. So does that kind of make sense for everyone? You can kind of see how that's structured, and like where the training is happening, where the graph definition is happening. Okay, so let's do while everyone continues to run their training. Let's do something kind of cool here, and that is to look at something called TensorBoard. So TensorBoard is a dashboard for looking at graph variables as the training progresses and comparing them, and it's a good debugging tool. It's really pretty nice, and to run it. So this, if you're running from the command line, just start up a new window in the same directory. And remember to activate, if you're running in a virtual environment, remember to activate that environment again, because you'll need it to find TensorBoard. Sorry, yeah. Okay. So this is just a new shell in the same directory. Activated the virtual environment for those who are going that route. Okay, so now I'm going to start up TensorBoard. And you pass it. So we'll look in a second at like just what are these summaries that this script is writing. In fact, it's writing some summary information. And we're going to point TensorBoard to that summary information, which is what I'm doing right now. And now it's going to start up a web server. And again, so you can just go to localhost port 6006 if you're running outside a Docker container. And if you're running inside a Docker container and using Docker machine, again, you need to type Docker machine IP to get the IP to hit. Otherwise, you can just go to localhost. Okay. On port 6006. And what you should see is something like this. And it's maybe not very impressive because in this case, we're only tracking one thing. We're tracking the change in the loss as the training progresses. But it's possible to track many more pieces of information and generate histograms and things like that. And before we dive into this further, one thing to comment on is you can also look at the graph. This is really neat. This is the graph that we're running.
Can we see that command again?
Yes. It was TensorBoard and then logdir equals, and in this case, this little script is hardwired to to write the summaries to this particular path. Yeah. And incidentally, that's in the, if you forget that and want to come back to this later, that's in the README for this directory in the repo. Okay. So here's the graph. You can see it better in your own TensorBoard server, but you can poke around and expand things. It's really quite nice. Okay, and then we also set up our script as it trained to log information about events. In this case, only the one event. And so you can see from this, you can compare across runs. Here's an earlier run I did. Here's my current run. You can zoom in and take a look at, say, how things are converging for a series of steps, and do all sorts of things. So I'm not going to have time to do it justice here, but it's a really nice tool. Like when you're building serious models that aren't quite so simple and need to do some debugging of how things are working, this can be really useful. Thank you. Someone reminded me to have 5 minutes before our mandatory break. All right, and I think that's good timing, because I think that we should probably be close to done with the training. Yes, okay, perfect timing. All right, so this is running this example for like 100K steps. And if you ran it for, say, 5 times as long, which you can, or even longer, which you can do by just going into the script and editing a hardwired value, you'll see even better results. But you can see that it's doing some interesting things here. You can sort of see where some of its values start to make sense. For example, it's cutting off the bottom too, isn't it? Yeah. We'll try to fix that during the break. So for example, with 9, it's clearly picking up on other numbers here. With the word American, it's Calothrix turns up peculiarly often in these lists, and it's actually related to I think it's a type of marmoset. So it kind of makes sense that you'd see Calothrix and marmoset in the same list. But setting aside the question of how that's related to these other words, you can see that American, English, British, etc., French. It's picking up on a lot of related words, right? So this is really kind of cool. Just by processing this data and kind of taking this sliding window along the data set, we're learning what words are semantically related. And in fact, you can look at a 2-dimensional plot of this. The script will write a file called tsne.png. And if you're running in the Jupyter notebook, it will display that for you as part of the notebook. So this is going to look too small, but hopefully you can look at your own and kind of navigate around it. So this is tsne is a method for doing a projection into 2-dimensional space of higher dimensional vectors. And so we can see how these words are clustering together, and we can see that similar words are clustering near to each other in many cases, which is pretty cool. So just to kind of calibrate, how is everyone doing on the training? Were you sort of stymied by needing to download that file and got delayed? Oh, okay. Oh, no. Oh, no. Still downloading. Okay. Maybe everyone can catch up during the break. You actually this whole workshop is designed so that if you don't catch up, no worries. Just go and run it at home with your higher internet speed, and you'll be fine. Did everyone get it basically to start running? Did people figure out their import issues? Okay, great. Okay, this is a good time for a break then. So it's, I believe this is meant to be about a 20-minute break or so. Seems like a long time to expect you guys just to sit here, but if you can come back in about 20 minutes, that'd be great. Okay, let's get started again. Thanks everyone for returning so promptly. I know it's not much of a break. Okay, so before we kind of switch gears and get into the sort of the last third of the workshop, I want to show you a little bit about how those summaries were working. So, and I want to particularly do this because this won't be, if you go and look on TensorFlow.org for the Word to Vec stuff, this won't be in that code. So the way we got that nice loss plot in TensorBoard was by collecting summary information and writing it periodically. And so I just wanted to show you guys what that looked like. So it involves doing some initialization and then adding some new graph nodes and then writing them, writing the summary information periodically. If you do it too often, it kind of collects a lot of data and can slow you down too, so you kind of want to decide how often do you want to write it. Okay, so here is where we're adding some, so this is the section where we're defining our graph. Here is where we're adding some nodes to the graph. And if you look at the information on the summary writer, you can get more detail about what's going on here. I won't go into detail, but basically we're saying we want to track the loss as we progress through our training, and we're going to track it and we're going to write it. Okay. So the step where we're initializing the summary writer is right here. So here we're creating it, and we're essentially just telling it what directory do we want to write this summary information to, and this is essentially kind of hardwired in to keep this example simple. So that's why the log dir that you pointed to is hardwired as well. But you can see how you change this. Okay, so this is in the context of running our session. We created the summary writer earlier when we were defining our graph. We added some summary related nodes to our graph, and then we have to, when we do session run, we have to now explicitly evaluate those new nodes, the summary related nodes. So in this case, just the one. So that's what's going on here. In session run, we want to evaluate this train summary op, as well as all the other perhaps more important stuff that we're doing. And we want to get the results of doing that evaluation, which is right here. Okay. So that's an important point, right? It's not just enough to define the node in the graph. You have to evaluate it if you want to do something with it. And then here is where we created our summary writer, and we're calling add summary. And we're passing it that summary information that we evaluated. And then just to kind of like go back and connect the dots, we're passing it the evaluation of this node in the graph. Okay, and so you could imagine that you could collect a lot more information than just the loss, of course. And if you look at another subdirectory in this workshop repo that unfortunately we're not going to have time to delve into during the workshop, you can see a more complicated example or more complex example of writing summary information, including building histograms and things like that. So that's the CNN text classification subdirectory. I know you guys probably can't see this in the sidebar, but CNN text classification. And I'll talk in a second. I'll talk just a little bit about what that does, because I hope you will go and play with it on your own time. And if you look at train.py, in that directory, you can see a more complex example of writing summary information. Okay. All right. So Eli and I were having a debate about whether we had time to do this next exercise, and because we want to be sure to leave time for the third section of the workshop. And I think we probably don't have time, but I want to encourage you to go. Let me just say a little bit about what it is. We tried to design the repo and make these fairly detailed READMEs so that you would be able to poke around with this stuff on your own. So hopefully you'll find it easy to do that. So the point of the exercise was, well, what if you wanted to track another word? So you remember when you were running the training, it sort of randomly picked a set of words, and then it printed out on each iteration what other words were nearby that word. So, but that was a randomly selected set. So what would you do if you wanted to like track a particular word, some word that you were most interested in? And so if you look in this the same directory, intro word2vec that we've been working in, and you look at that other script, word2vec basic nearby. That shows you how you would do that. And unfortunately, there's not an IPython notebook for this. Oh, and incidentally, I think Eli and I reached the conclusion that the issue with the IPython notebook was like a 2.7 versus Python 3 incompatibility. Sorry about that. So we'd kind of like this to work with both versions of Python. So we'll add some more comments and things to uncomment out if you're running in 2.7, and we'll check those into the repo. Okay, so back to this file, word2vec basic nearby. If you take a look at it, you can see how you might add additional nodes to the graph to track a particular word. And here's an example of how you do this. Look for the word government in the file if you're playing along. And essentially, it's just it's almost a cut and paste modeling of the tracking that's already being done with that graph for that additional or for the original set of words, right? The randomly picked set. And so we're just saying let's just track one more. Let's calculate the nearby words for that additional word. Let's evaluate this new subgraph also when we do session run and print out the information. And so it's as far as the TensorFlow ops go, it's the same ops, so there's nothing new there. So it's just kind of intended to get you a little more comfortable with building out the graph and evaluating nodes. And so if you have time to go play with that, or at least look at the example, I would encourage that. Okay. So let me talk about one more thing before I turn it over to Eli. Okay. So this is a whole. I might come back and do this demo if I have time. But what I would like to talk about is sort of a whole additional section of the code in the repo that we knew we wouldn't have time to get to, but we wanted to include because we thought it was just so fun and so cool. And again, kind of in the hopes that you can take this and go play around on your own time if you're interested. So there are some research papers that explore using convolutional neural nets for text classification. So, excuse me. So the idea of a so-called convolved feature, and you often see this with like image processing, for example, is you learn a filter. Maybe it learns how to detect edges, for example, and it really is just needing to know local information, right? So you've got this n by n filter that's sort of passing over your image. And it can detect edges the same, just if the edge is in the upper left or the lower right. It doesn't really matter because it just needs the local context. And so the neural nets, the convolutional neural nets that people build to learn these filters. I won't go into the details of this now. Sorry, we're so short on time, but the links at the bottom of these slides give you some additional reading. So the idea is that you define neuron groups, for example, A, and you can essentially to learn these convolved features, and you can kind of stack them up, essentially letting you learn higher level features at higher level of abstraction, right? So your lower level convolved filters might be looking for things like edges, and as you go up the hierarchy, you might be able to detect, oh, this is some kind of mammal, for example. This is a cat, maybe way up at the top. And so, and if you go back and look in the slides at that big schematic that I showed you that I said was this Inception 3 graph used in the ImageNet contest, that you'll see that from that schematic that it's doing a lot of convolution. So TensorFlow has powerful operators for doing this kind of thing. And there's, as you build up these layers of your neural net, there's a concept of max pooling, which essentially kind of collapses or folds a given layer of the neural net into a smaller space by as you can kind of see here, taking the max of a set of subareas, each of a set of subareas. So you start to get networks that look like this. They're actually usually not just one-dimensional, so you start to get things that look like this, etc. And finally back to the Inception 3 graph. All those, you can't probably read it, but convolution is this sort of beige color here, and you can see there's a lot of it going on in this 40-plus layer graph. Okay, so I apologize for that being such a quick overview, but again, there's lots of links to reading if you want to learn more. But the interesting thing that kind of relates to what we were doing with Word2Vec is there's been some research on, well, how does it work to use convolutional neural nets to learn text classification? And so the way people tackle this is they set up a big word embedding matrix, which is kind of like roughly indicated by this this first block here, and run their so it's the same thing we were talking about with our other exercise in terms of word embeddings, right? Your words map to these vector representations, and you can do your you can run convolutional filters over that matrix. And so this actually works surprisingly well, and there's some links to more details if you want to read about it. But what we have included in the repo that we hope that you will play around with if you're interested in is kind of a fun application of that. So we have an adapted version of convolutional neural net for text classification code, not built by us, built by a guy named Denny Britz, who has a nice write-up that goes along with it. And we have, so you can run that. And we've provided a data set that actually comes from Reddit, so where you're learning classifications of subreddits, essentially. And so you can run that code, it's in the repo. But then the next kind of logical question might be, since you just did training that learned these word embeddings, it's like, well, what happens if we don't just start from scratch with this network, with learning our word embeddings? What if we initialize this this matrix here with the semantic information we already have from our previous training? And so it turns out, which is kind of a cool thing to observe, that it helps the training. You get better accuracy faster, and your loss is lower. If you run it for long enough, I think it starts overfitting and kind of everything converges. But you see a very clear effect at the beginning, which is really fun. And so all of this, there's detailed READMEs in the repo, and that's what all of those data files that we had you download are related to, or most of the data files. So,
Amy, could you go
yes.
back to the slide with the link to Denny's?
Oh, yes.
I
And
don't think,
that's in the README as well.
okay, that's in
Yeah.
the README. I don't think
Yeah.
they have that in the, yeah.
Yeah, it's in our repos README.
Great.
Yes.
Okay, thanks.
Yeah. So we're running we're not running his exact graph. We're running a modified version of it so that we can do this experiment of what happens if we initialize that big embedding matrix with the vector representations that we learned. So his original just initialized the embedding from scratch. So we've added a kind of a twist on that, where what if we have learned embeddings? What if we initialize that embedding matrix with those learned embeddings? What happens? And so we hope you'll sort of mess with that if you're willing to download those big data files. And this is a graph which is probably not showing up very well. No, it's not. you can see it in the README for this subdirectory, and you can see a clear effect, especially at the beginning of the training, where the version that's using the initializing with the learned embedding, so it kind of has a semantic leg up, so to speak, on doing the classification, does better. And we specifically trained, since this exercise is using Reddit data, we also specifically trained, did a version of Word2Vec, which also used Reddit data, because you kind of imagine that Reddit, subreddits would have their own vocabulary, and indeed it kind of turns out to be the case. Like if you use embeds trained on Reddit data, it does better than embeds trained on just sort of like, say, generic Wikipedia data. So that's all kind of fun to play around with, and we help you with that. Okay. And this was just to remind me, I probably shouldn't have called it a meta exercise, but it was just to remind me that to mention something specifically to you. This this net and the train.py that goes along with it is a good example of how you can checkpoint and save model variables and the model graph, and then reload them and use them later. So that is very straightforward and possible with TensorFlow. And this just for lack of time, the stuff that we've shown you so far didn't really get into that. But it's very common that people would do this. As they're training, they'll checkpoint regularly. And there are even some TensorFlow classes that kind of do some of the bookkeeping of that for you, or you can just kind of do it manually. And you can save just the variables, you can save the variables and the model graph, and then you can load them in later. And so this is good not only for doing prediction, of course. You want to use your learned model later. maybe you want to load it onto an entirely different computer. Maybe you want to run it on your Android phone. But also it's useful for recovery, of course. If your training gets interrupted, you can pick up where you left off. So take a look at in that directory. Take a look at train.py to see how that information is getting saved, and then take a look at eval.py to see how it's being loaded and used. And so that's a good example of that. All right. And so we're about to switch gears and talk about the distributed runtime. So to kind of wrap up, I hope you you sort of got the idea that there's stuff lurking in the repo that might still be fun to mess around with. It was sort of beyond the scope of this workshop. And we're really interested in feedback on that stuff as well as you know, as well as what we had time to cover here. So if anyone does play around with it and has questions, or you know, wishes something was covered in a little more detail or whatever, please get in touch. Probably the best way to do it, since it's on GitHub, is just, you know, open an issue with us, or something similar. We can't. The repo is not currently set up to accept pull requests, although we might be able to change that in future. Okay. Are there any questions before I let Eli take over and turn into the roving TA? All right.
So there is a section in the workshop repo, distributed runtime, which has instructions in it for setting up. So I'm going to, I don't know if any of you followed that on your own. You didn't necessarily have to. It should be a relatively quick setup. So I'm going to give you some time now to do that. It does require, technically it does not require, but the easiest way by far is going to be to set up a Google Cloud Platform account. So obviously you will be able to get a lot out of this section without doing that. You don't have to do that by any means. But if you're interested in doing that, I'm going to give you a little time to do it now. And I'll take any questions about difficulties doing that.
And let me just say, it's suggested that you create a cloud platform project. And so if you've never, so if you want to do this and you've never done it before, be sure to sign up using the free trial, which means this won't cost you anything. And if you have already set up a free trial, and
yeah, so
I know.
this is for fraud prevention. That credit card will never ever be billed. So you have to explicitly say, I want to convert to a paid customer, and then it will run out the rest of your $300. But yes, it is an unfortunate. People really like mining Bitcoins on Google Cloud if we don't require this. So
if you have already set up a free trial and you've run it out and you want more credits, raise your hand and I can give you more credits, so that this definitely doesn't cost you anything. So I saw one hand. Is anyone else? Okay.
So if you could just like raise your hand briefly to let me know when you've completed those steps, or how many people are just roughly interested in following along. I can also skip this. Okay, so it seems like a fair number of you, so I'm going to shut up for a little bit now.
Okay, so here's a coupon code that you should be able to use. Yeah.
I think there's a section in the billing page. So if you go to the account for your billing account, if you've already opened a free trial account and it has run out, you can go in and there should be a section somewhere that says add credits. And if you click that, there'll be a place for you to enter a code that we give you. Yes, I think so.
And if anyone is trying to set this up and has issues, just raise your hand. Again, you can just watch along if you don't feel like doing it.
Just going to do a couple more minutes. Is anyone done with the setup yet? Hands? No. Okay, so maybe.
How many people are attempting the setup? Oh, great.
Yeah, okay.
Okay. Good. You can turn it on.
Sorry? Yeah, so there, below the section where it tells you how to create, so there should be a description in the README that says go and create a, yeah, so this is the README for the section, the distributed TensorFlow, or section in the workshops. Yeah, sorry. So you'll end up creating a container engine cluster, which is Google's hosted Kubernetes. And actually, if you're feeling adventurous some other time, Kubernetes is platform agnostic. So you can go and run it on AWS, you can run it on-premise, and you can try setting up this tutorial elsewhere. GKE just happens to be the fastest and least error-prone way to get Kubernetes cluster running. Is anybody stuck? Are we still, things are working as expected? So while people are setting up and finishing setting up, I'm going to talk a little bit. We won't actually get into the demo where you have to follow along for quite a while. So you have plenty of time to finish the setup if you're still working on that. So the reason we're talking about distributed TensorFlow is because you're all now TensorFlow experts. And so because you're TensorFlow experts, you're writing really big models that operate on really big data sets, and it's making your laptop very hot, and then you're moving to a server rack, and it's making the server rack catch on fire, and you're moving to a GPU cluster, and it's still, or you're moving to a single GPU, and it's still problematic. And eventually, you're going to need to distribute your model. And so that's just kind of a fact of scale. If you look at Inception and you try to train Inception on a single machine, that's the 40-layer model we showed you earlier. It's going to take a really long time. I'm not sure exactly how long, but I think it's at the very least days on a reasonably sized data set. So if you want to be able to build big models and train them on lots of data to get very high accuracy, it helps a lot to have a distributed framework to do that. So where does Kubernetes come into this picture? Well, Kubernetes is another Google open source project. If you're not familiar with it, it's a container orchestration framework. So basically, a lot of you are familiar with Docker containers. They're a convenient way to package things up and sort of namespace processes on your system. However, if you're running a lot of Docker containers, you run into the same problems over and over again, which is, how do I deal with storage? How do I deal with, startup and networking those Docker containers together? And this is where Kubernetes comes in. It's basically an abstraction layer that sits in between the nodes of your cluster and your Docker containers. And so it's an API that you talk to. It contains sort of like concepts that that are opinionated about how you write your application, and force you to sort of write it in a way that the cluster can be agnostic about it. And it's a really convenient way to work with distributed systems in general. So in this case, TensorFlow, the distributed runtime, uses gRPC, yet another Google open source project. So we're using 3 different Google open source projects. It's pretty cool. It represents, a huge amount of investment that Google has put into open source. And gRPC is Google's remote procedure call framework. It's an open source version of what we use internally called Stubby, and it's very fast. So it over HTTP2, so it supports streaming. And it's used for this because in TensorFlow, you're often passing around very large objects. So being able to compress those when you send them over the wire is very important for performance. So gRPC has client library bindings in, I think, 7 different languages now. So the TensorFlow runtime takes advantage of those client library bindings in Python, obviously, and provides us with nice sort of high-layer abstraction for running TensorFlow servers, which can receive instructions about ops they're supposed to run, make updates to variables that live in the cluster, all those sorts of things. So this is sort of the broad structure of our cluster as we created it. So the kube control create -f command that you ran created all of these objects in your cluster. And they fall roughly into 3 different groups. So there's the server, the Jupyter server, and the TensorBoard server, which is how we're going to interact with the server or with the cluster externally. So we're going to write programs in Jupyter that are going to execute and be delegated to the other containers in the cluster. There's PS, which is the parameter servers. What these do is they serve variables to the rest of the cluster. So they serve as a synchronization point for the cluster. And it's not intuitive as to why you would want multiple parameter servers, but I'll cover that a little later when we do the walkthrough of the example. And the third kind is workers, which can receive TensorFlow ops from the master and process those operations and make updates to the parameter server. So you'll see they're all interacting through gRPC. And in fact, this is a fully connected graph. So at the beginning, when you're declaring these things, the graph, every worker needs to be aware of every other worker, and every parameter server in the master needs to be aware of everything. So as you can see, I've actually set up this cluster also runs a TensorBoard server that will pick up logs from your Jupyter container. Before I move on, any questions about Kubernetes in general? Why cluster? Why Docker containers? No. Okay. So because this is, not an ops workshop, it's a machine learning workshop, I'm not going to talk too much about the Kubernetes. We're not really going to talk about it at all. We're going to let that nice abstraction layer take care of all that stuff for us. Instead, I'm going to talk about what you need to do with your model in order to parallelize it. So there's a lot of choices you have to make that depend on the size of your model, the ops in your model. And these break down into two different categories and a choice in each category, roughly. So the first is model parallelism, which is basically how do you decide which ops sit on which machine? So the first option is to just do everything on every machine. This is a pretty popular option because the code that you write ends up looking very similar to the code that you write for a single process training job. And that's nice. It makes it easy to verify models and then easy to ship them to the cluster. So what we have here is we have a tf.train.server. So we're giving it a cluster definition which has addresses for all of the workers. And we also need to tell each worker who it is in the cluster because this is, again, identical code that's going to be running on each of the workers. And then the worker can use its identity to sort of decide what it does. So if it's a parameter server, it's just going to wait and receive ops or receive variable updates from other nodes in the cluster. If it's a worker, we're just going to run sort of whatever we would run in the single version. One thing is we need to pin our variables to those parameter servers because we don't want the workers each having their own copy of the variables because then you're not actually training, you're training 14 different models. You're not training one model with 14 different workers. And so how we do that is there's a handy tf.device context manager. And what this does is it pins all the operations in the graph under that context to the device you specify. tf.train.replica device setter is actually just round robins all the variables declared in that context to the parameter servers in your cluster. Could I actually get this down a little bit? I think I can talk a little louder. So the next thing you're going to do is once you've assigned all the variables, you need to figure out how you're going to coordinate once per cluster tasks. So these might be the supervisor that Amy showed you earlier, or this might be the summary writer that Amy showed you earlier. So you're writing summaries out to a TensorBoard server. You don't want to do those for every single worker. You don't want 14 different copies of your logs, basically. It might be checkpointing, which we didn't get the chance to show you, but is in that CNN example. And it might be initializing parameter servers. So you don't want to accidentally overwrite work by initializing the variables with your different clusters 14 different times. So this is what that looks like. You have a supervisor, and you use, again, that sort of identity that you gave the worker to determine whether or not you're chief, so whether or not you perform those once per cluster tasks. And then you run normally not, this is the same code that runs on every one, except the once per cluster task will only be executed if you told the supervisor that you were, in fact, a chief worker. So the other way you can do model parallelism is a little bit more fine-grained. It's, what if we want to have one graph, so one context here, and pin individual operations in the graph to specific workers? So this is what that looks like. So for example, if you wanted to do an independent loss calculation on every worker, you could do something like this. You could say, for every worker, pin a loss operation to that worker. And the cool thing about this is the TensorFlow distributed runtime will take care of shipping the tensors across the wire to the appropriate device if you do this within one graph. So for example, if we had upstream tensors above this statement here that we needed in order to calculate loss, and we had those just on a single machine, the distributed runtime would take care of sending those to each worker. And you'll see that in action later in the demo. So the other advantage of this is that you can use a single synchronized training step. And so the more awake among you may have realized that I've sort of glossed over a very important problem in distributed computing, which is how do you synchronize things and make sure nobody steps on anybody's toes with respect to variable updates. And so that's the next kind of choice I'll be talking to you about. So here you'll see on a single worker, which we've called master, we average all the losses and we feed them into a single training step. So we're not duplicating the work because optimizing an average loss is the same as 14 separate times optimizing in each individual loss, right? The minimum of the average is the same as optimizing the minimum of each individual. And then what we do is when we make our session, we have a specific master, which tells the cluster basically which, this is how, if you're doing subgraph replication, you determine which worker is going to do once per cluster tasks. So this is, the master address, and we run it, just like we would run an individual single worker. So about that synchronization. So there's two different ways. So data parallelism is sort of the separate second choice you need to make. It's the other axis along which you can evaluate how to distribute your model. Asynchronous training is when each worker is running an independent training loop. So for example, in the full graph replication we saw, each worker was running an independent training loop because each worker had an independent session. So there was no real way that they could coordinate the training. So what you'll see here is there are, a set of parameters, and each worker, maybe the worker on the inside here completes 3 different gradient calculations and applies the gradient 3 times to the variable before the outside worker does it once. So this can potentially create problems. You can imagine if you have a very large model and you get very out of sync, the back worker may be working from like a smaller piece of the data, and so the updates it may be applying may work in contrary to the other updates. So you can sort of imagine, like, for example, gradient descent is setting a marble at the top of a hill, right? And like watching it roll down. But if you have 8 different marbles, it's great if they're all in the same place to sort of average the direction of movement. But if they get spread out, like what happens if you put your 8 different marbles on the ring around the top of the hill? Well, all the vectors that they're traveling in average out to 0, and you never go anywhere. That's sort of an extreme contrived example, but that's sort of some of the problems you might face with asynchronous. In many cases, when you're working with smaller models, asynchronous training is actually fine. And it actually may be advantageous because you're not forced to wait for each individual worker to complete. So asynchronous, each worker can go as fast as it wants. Synchronous, you're effectively pinning your cluster to the speed of the slowest worker. And so if you've done your scheduling poorly, for example, and you have a bunch of workers on a single node, or if you just have one node that's being a slowpoke because of network connection or something, you'll be punished for it if you do synchronous. Synchronous does have some advantages, though. Again, like I mentioned, you don't necessarily have to worry about your workers diverging. So this is what we showed earlier. You do expensive computation on every worker, for example, computing a loss, and then you bring all those gradients together and you average them, or you bring all those losses together, average them, or sort of anywhere in the pipeline you can have a synchronization point. So obviously this is much easier with a in-graph or a subgraph replication model. However, there's a specialized optimizer that TensorFlow provides that can actually synchronize in a full graph replication. So if you write code that every worker runs, that is the first option. There's a special optimizer that the library provides that will synchronize your training steps across the workers, even though you've written the same code to run on every worker. Another advantage of synchronous training is that you can take advantage of all that subgraph replication that I talked about earlier, where for very large models, again, you may have parts of the graph that are bottlenecks, or parts of the graph that can be more effectively distributed than other parts of the graph. And so what might be nice to do there, why subgraph replication might be advantageous, is to sort of split that part of the graph into mini workers and then unify it when you're up to speed, basically when that part of the graph is no longer a bottleneck. And synchronous training can take advantage of that, as you see here. So like, for example, if loss computation is the bottleneck and it's very fast to compute gradients, you can compute the loss on a bunch of different workers, and that's effectively like computing the loss on a much larger batch size. And that's data parallelism, which I'll talk about, which I'm, title of this slide. So data parallelism is I have split my batch of training examples, for example, into a lot of different pieces, and I'm shipping one of those pieces to each worker. So the loss is computed on a mini batch, as we call it, and so you can effectively have a much larger batch size when you're averaging those losses. And so, for example, if you're training a very large model that has extremely large embeddings, so if the embedding size for our words instead of being 128 was 1024 or something, your nodes would potentially run out of memory. You'd have all sorts of other problems due to the batch being too large. And if you needed to do that to get more accuracy, it might be better to split just that piece of the graph and then unify it later. So kind of summarize that fire hose of information. Two different choices you have to make. Model parallelism, which is where do I run my operations? So subgraph replication allows the fine-grained application, so you can pin specific ops to specific workers, and this is useful if you have bottlenecks in your graph, if you have a very large model. It's also easier to do some kinds of data replication. Full graph, the advantage is you're writing code that's very similar to the single process, but for large models, you may not necessarily see as much performance gain because you have these bottlenecks. For data parallelism, if you do synchronous updates, you are moving at the speed of the slowest worker. If you do asynchronous updates, you're sort of risking your workers stepping on each other's toes. And also these affect sort of how easy it is, or they affect what it looks like to split your data into batches. So hopefully some of that stuck in. I think the most instructive thing is going to be to see this in action, what it looks like to run through some code. So this is the point at which hopefully you've got, hopefully you've got a working IPython notebook, unlike me. Okay. Seems we have some restarts here. Okay, that looks right. This is actually, I'm just going to present from a not running notebook. Hopefully, you've successfully uploaded the intro word2vec distributed file to your running Jupyter server. Can I get like hands who has successfully made it to this point? Excellent, like 3 people. Yeah, so So I think it'll be fine for you guys to see sort of what's going on here. Those of you who have done this or want to do it later, the instructions are sort of self-contained. And all of this stuff sort of from here to here is more or less the same as the single process version of Word2Vec that you guys encountered earlier. So here, all I want to point out here is that Kubernetes has done us a favor in injecting this gross cluster configuration as an environment variable into our Jupyter server. And also that TensorFlow has its own format for device finding, basically. So it uses this cluster spec and it builds like a dictionary of devices to addresses that the gRPC server uses. And so if you want to address a specific device in your cluster, you can simply go, /job worker if it's a worker, or /job PS if it's a parameter server. And it will know to pin ops to that device. So this is me just building up a list of workers and parameter servers for use later. These are actually the exact same hyperparameters. There is a lot of implications that distributed TensorFlow can have on the hyperparameters you use. Because this is sort of a toy model, we haven't really changed anything. But it can be very instructive to change the cluster configuration and then watch what you need to do to the hyperparameters in order to get sort of a similar result. You can learn a lot about machine learning doing that, or you can break a lot of things, which is what I did. So here's where things get very different. So we started defining the model. It looks the same from here. We made a TensorFlow graph, and we're sort of entering the graph's context, and we're going to make a bunch of operations. This looks very familiar. These are the same placeholders that we had to get input into our Word2Vec model previously. But then what we're going to do is we're going to do some data parallelism here. So we're going to actually split each of these batches. So in this case, we have 8 workers in our cluster. We're going to split each of these batches into 8 different pieces, which is going to be like 32 sized pieces, I think. So individually, each worker will be handling much smaller vectors or tensors than it would have previously. We're actually going to create a number of embedding variables. So this is interesting. Remember when I said it's not intuitive as to why you would want multiple parameter servers way at the beginning of this? This is where we take advantage of that. So we're actually going to be tracking embedding, again, Word2Vec. We're taking words and we're putting them in a higher dimensional vector space, so turning them into vectors of length, in this case 128. And then those vectors, when the words are similar, are close together. We're going to actually track, in this case we have 4 parameter servers, we're going to track 4 different versions of those embeddings. But they'll all sort of converge because we're going to parallelize fetching those parameters. So these are the same weights and biases. We're just assigning them to random parameter servers. But here, where we do an embedding lookup, and this is true of a lot of the operations in TensorFlow, is they're sort of, we've been using it in a distributed context for a long time, so we want distributed computation to be a first-class citizen. So embedding lookup, if this embeddings is a single tensor, it does a lookup of the embeddings in that tensor. But if it's a list of tensors, it grabs sort of columns in the tensor in parallel from each different embedding in the list. So effectively, we're grabbing, like, if you imagine the embeddings as like this 128 length vector, and we have 4 different parameter servers, if it's 0 mod 1, or if it's 0 mod 4, then we get it from 1. If it's 1 mod 4, we get it from another. So we're grabbing little pieces of each of these vectors. And that's faster because we have to grab smaller amounts of data. And also it allows us to keep these independent embeddings, which provide a little bit more robustness to our model. We're learning sort of in 4 different sets of embeddings at a time. So then this is the same loss computation. Exact same TensorFlow op. And you'll notice we're doing all of this on each worker. So we're doing that parallel embedding lookup on each of the 8 workers we have. And we're building up a list of operations. So remember I said that these return values are pointers rather than the actual operations themselves. This is important here because obviously this operation actually lives on another device, or will live on another device. And then we're also going to write a summary, a TensorBoard summary, for each individual worker. We're going to write its independent loss so we can see how the individual workers are working. So then we're going to go back outside of the context of stuff we're doing on every worker. We're going to average out all of those losses. And we're going to do a single unified training step. So by now it should be clear that this is subgraph replication and it is synchronous training. So these are maybe actually not the choices you would make were you training this model yourself, but I wanted to show them because they're sort of the most complex examples and they diverge the most from the single process training mode. So if you were to write this yourself and want to distribute it, you'd probably take something very similar to the distributed example that's on the TensorFlow, in the TensorFlow repository. So all that does is it basically takes some code and it has a supervisor, and then you run the same code on every worker independent of each other. They have independent sessions. So this training op, we have a global step here also, which keeps track of, so it's not super important because we're doing synchronous training, but if you were doing asynchronous training, this is how you would get all the workers to tell you know, whatever monitoring system you're running that they have contributed a step to the training process. So this is a variable that lives on a parameter server that all of the workers can each update independently. So if you had 8 workers and you were doing, for example, asynchronous training, then each of them would increment global steps, so you wouldn't have like 8 times the number of steps you expected, or you would have actually no idea how many steps had elapsed. This is for actually the reporting of similarities at the end. So we have 4 different sets of embeddings, so we're going to have to average the embeddings to get the final embeddings that we want. But because they're being trained together by this parallelism, we know that averaging them won't get us like crazy results. They'll be hopefully pretty close together. All right, so what does running distributed look like? Well, fortunately, so this is probably not going to work because I'm still, for some reason, not connected. At the end of this, I'll refresh just because I'm afraid it's going to disconnect me. Fortunately, as I mentioned before, we try to make distributed as easy as possible. The code for running a distributed session looks almost identical to the code for running a single process section. The main thing you'll notice here is we've sort of connected to the worker that we want to specify is master in the cluster. In this case, I've set up the Kubernetes cluster so you have one of the TensorFlow workers at localhost to your Jupyter server. This should look all very familiar. A summary op. One thing to notice here is that instead of tracking the number of steps with a local variable, we're actually evaluating the global step variable and using that to keep track of the number of steps. Again, not necessary in this context because we're doing synchronous training. But if we were to be doing asynchronous training and independently updating this global variable, this would allow us to halt training, when we reach the appropriate number of steps. And this is the same reporting process as using before. So I'm going to try refreshing this now. Oh, that's probably why it disconnected me. Password. Great. Okay. Questions?
I was just saying, I tried step 5 and I just crashed.
Are you crashing with a common error? Hopefully. Should get together. Oh. Hopefully there's no saver in here. I wonder if I don't have the version from the repository. Okay. I will follow up afterwards, unless, Amy, you think you can debug it. It might be that I left some of the saver code in. Hopefully not. If there is a line that references a saver anywhere in the... Yeah. I might have accidentally pushed the wrong one to the repository. Oh, unless, when did you pull down the repository? Can you do a git pull and upload the new one? Yeah, that might also be it.
We may need to fix this after. We'll do it shortly,
Yeah.
and you can try to.
So mine, fortunately, started training. Hopefully we can get everyone on the same page. And you'll see we have average loss decreasing. One thing I want to look at is this is pretty cool. This is Weave Scope, which is an overlay network for Kubernetes that allows you to look at some network configuration. So just so we can get a sense more of how things are interacting, of course. Oh, my mouse. There we go. Cool. So we can get a sense of how things are interacting in our cluster. It's not actually a fully connected graph. So if we go in here, we zoom in, we can see this is network traffic. These are connections, so durable connections. This is using gRPC streaming. And you can see that the parameter server is talking to each of the workers, but not the master. And you can see the worker, because remember we're doing that parallelized fetch from each of the parameter servers. The worker is talking to each of the parameter servers, as well as the master, but not any of the other workers. So again, the distributed computation sort of synchronizes through the parameter servers, which are storing this variable state. And of course, as you would expect, the master sort of talks to everything. This is where our Jupyter server is running. And hopefully, if my scheduling did a good job, I should have fairly high utilization on each of my nodes. That's not great. All right, so a scheduler could have done a better job. C minus. All right, so the other thing to mention is we have this TensorBoard server running. And we should see an old run that I did previously. So this is just to show that all of the things that you learned about in the single process are still applicable. And remember, Amy was mentioning you can write a lot of different summaries out. So in this case, we wrote a different summary out for each of the workers. So let's just look at the most recent one. So we've averaged the loss across all the workers. And you can see, because the workers are all working with a smaller batch size, they're working with mini batches, they have a much higher standard deviation in their loss. It's going up and down a lot more. But because we're training on the average loss, that's OK. Because you see the average loss sort of evens all of that out between the workers. All right, so that's distributed, kind of a whirlwind tour. If you have any questions about any of the workshop, you're welcome to ask them now. I think that's what we have for you. Questions? Question? Mm-hmm. Yeah, in fact, no kubectl commands should be necessary. You should just be able to delete the cluster entirely, the container engine cluster. Yeah, so that's, I need to look at the
Although
README.
if you want to just delete, the pods, et cetera, and not take down the cluster, you can do that. Yeah.
Yeah, it's just if you replace, it's like kube control create dash F the file to create it. It's just kube control delete dash F the file to delete all the resources. So if you want to keep your Kubernetes cluster to play around with. Other questions?
I think we probably, fire hose you into numbness at this point. It's a long workshop for so much information as we threw at you. But please do take a look at that repo for more detail and everything. Yes, you had a question.
I guess besides the repos that you've provided,
Mhm.
is there other places you recommend to find other sample projects?
Yeah, so the question is where to find other sample projects to look at. So the TensorFlow.org is of course a really good place for that, and they're adding more tutorials, like every month there. But additionally, if you just go online, people are playing around with TensorFlow, and they're creating GitHub repos for what they're doing, and they're blogging about it. And just doing some simple searches can actually flesh up a lot of interesting stuff where people are experimenting with different things.
I believe there's a Udacity course for TensorFlow
yes.
now too.
Yeah.
If you're interested, that was written by a couple people on the core team, and it's quite good.
Yeah.
It does assume some familiarity with ML concepts, but it's quite a good workshop.
And I think TensorFlow.org links to that, doesn't it?
Yeah, it should.
Mhm. And there's also a discussion group, I believe TensorFlow-users, a Google group, where you can find a lot of people asking the same questions you have, and also get information about like what people are playing with and what they're trying out.
There's also lots of resources if you're looking to get more into machine learning generally.
Mm-hmm.
The Coursera course is actually fantastic. I would recommend that if you're looking for a very high level overview of machine learning. There's a book that's coming out quite soon, which is a little bit more deep dive, particularly into deep learning from the perspective of a Google author that I can find a link if you track me down afterwards. Or I'll put it in the GitHub repository under the resources. Yeah.
And on a lighter note, if anyone didn't get a TensorFlow sticker and
Oh yeah, there are stickers.
come up here. Okay, thanks very much.
Thank you.
Thank you.
Very hard topic to explain.
Especially in 3 hours.
Yes, please. Uh-huh.
Yeah.
Uh-huh.
Yeah, so CloudML uses TensorFlow graphs as
Yeah,
basically as the thing that you ship
absolutely.
to
Yeah,
the Google API that runs them, that trains them. So
I'm not
basically
sure
the
if there are
API
any
is like a REST
mics on.
API for serialized TensorFlow graphs that you set. And this is all quite subject to change. It's all very early stages. It'll actually be good for larger problems because it's going to take advantage of Google's internal